谢谢。So let me introduce today's speaker first. Stone Tao is a first-year PhD student at UC San Diego under the guidance of Professor Su Hao. And his research focuses on developing efficient, adaptable, and capable embodied AI. So his work primarily addresses scalable data sets and benchmarks for embodied AI, especially at the intersection of simulation and machine learning. So today we will focus on discussing ManiSkill, which is a highly efficient and also a realistic robotic simulation platform. So although earlier in his PhD, Stone has been deeply involved in the development of ManiSkill, from the first version to the third version as well. So and he currently oversees its maintenance and updates. And we look forward to today's discussion. And the stage is all yours, Stone.
Yeah, thank you. So I'm a second year PhD now, advised by Professor Hao Su at UC San Diego. Most of today's talk is more of kind of two things, talking about why we are doing this kind of research, and how we are trying to tackle the problem of scaling simulation for embodied AI, as well as kind of just like a high-level overview of what ManiSkill, our simulator, provides, as opposed to other simulation benchmarks. So I kind of want to start this presentation with just a very high-level motivation overview. I think, obviously, as everyone knows, there's a lot of big amount of hype around humanoids, general purpose models, vision language action models, VLAs. And as we know from like training large language models, right, the same old dead horse, lots of data and good models, right? In the case of language models, we have the internet data sets, proprietary data sets, right? OpenAI, Anthropic, and whatnot. And then they train with a pretty standard like transformer kind of model. In robotics, we also have the kind of same paradigm emerging now, right? We have massive real-world data sets like OpenX embodiment, Droid, RH20T, and we also have some recent popular, VLAs, Octo, RDT1B, which got released 2 weeks ago, and Robotics Transformers 2 from Google, etc. But notably, actually, a lot of research recently is kind of like this. Most of the recent research you'll see online on Twitter, ArcSiv, and all the news is all about models. Octo, RDT, RT1, X2, LAPA, OpenVLA, Vima, GR1, now the GR2, PalmE. There's a ton of different vision language action models. And for the most part, I would say they're all making, fairly incremental improvements. Not bad, but, not significant groundbreaking progress just yet. But, in terms of data sets, we just have a couple big ones. And even then, they're not even that big, right? We just have the same amount of data sets. So what is the problem here? Well, learning from language models, right? The things that we really need to make these big models super effective for general purpose embodied AI, to make them easy to fine tune and whatnot, is data. If you ask anyone at the frontier companies at OpenAI, Anthropic, Google, most people will say what defines their language models is their data set, not the modeling. So models will do better. Models will help us use less data. They're better at fine tuning. But in reality, in my opinion, I think a big chunk of unexplored research is how can we increase the data we have at hand. And this is what we really need, right? This is I think, in my opinion, what really should be done in terms of research right now. How can we get more data? We can have great models, but every single time there's a new model out there, a new paper about VLAs, it always often comes back to the same problem. Get more data, do more pre-training on that data, and then all of a sudden your downstream model is a bit better. And so now the kind of question that I'm trying to pursue a lot recently is, answering that question mark. What is the next big data set we can make, without having to spend copious amounts of time and money, to further progress the state-of-the-art vision language action models. And just to further highlight this kind of problem with data, I mean, everyone's aware of that robotics data is hard to collect, but now a lot of people are kind of aware of how much magnitude of a difference there are. So let's just take a look at two of the biggest data sets right now. The biggest robotics data set out there, I think, is still OpenX data set, if I'm not incorrect. They have about 1 million, give or take, different robot demonstrations. Each demonstration having about, let's say, 100 tokens of data. This is very small in comparison to, kind of one of the smallest internet language data sets, which is a Common Crawl data set, composed of Wikipedia, Reddit, and whatnot. There's a 10,000 times size difference between the smallest language model data set and the largest robotics data set. And this is a pretty big gulf to gap to kind of cover. And this is not, if you also consider the fact that, frontier language models will train on probably 10 trillion to maybe 50 trillion something tokens. And then also the fact that the OpenNext data set has a lot of very, very similar data, a lot of pick and place, not too much diversity. This difference is actually not 10,000x, it's more like maybe 1,000,000x times smaller. And so, a big part of my talk today will be kind of trying to convince you guys and discuss about, how we really want to bridge that gap in data set size. Modeling could be one thing, it's important, but we need to get more data to model on, right? And if I'm speaking too fast, or if anyone has any questions, feel free to stop me, put a message in the channel, and I'm happy to stop and answer questions. My presentation today is not super long, because again, it's the same answer to almost every problem, I think, in machine learning, which is how do we get more data? That's what I'm talking about today. Okay. So there's a lot of research recently, in real world teleoperation, right? A lot of people using the teleop tools from my adjacent lab at UC San Diego from Xiaolong Wang's lab. A lot of people are using the UMI grippers, right, from Shuran Song's lab. And you also have all these other kind of teleoperation like Jello from Berkeley. So I'm not going to say real world data is not important. It is still very important. And I argue we absolutely need it. But I would also strongly argue that real world data should never be our largest data set. It should be better seen as like the cherry on top, the fine-tuning data set, sort of how we perceive preference data and supervised fine-tuning data for language models, expensive but very valuable data, but not necessary, to like produce the best language models. The pre-training data set, however, is something that we need to be able to scalably collect. And the biggest reasons why we want to use simulation is purely about data quantity and diversity, which I'll explain. Obviously in the real world, right, real world teleoperation, the number of frames of data you can collect per second is fundamentally limited by the laws of physics and how much money you have. If you have $100,000 and 1 year of time, you can get yourself maybe 5 robots, right? 5 Franca arms, and collect what, 10,000, 20,000 trajectories in 1 year, just nonstop. If you're lucky, you can get maybe like 30,000. But there's a lot of problems, right? With real world data sets, you can't reset states. It's slow to teleop. If you are trying to, let's say, teleoperate pouring water into the sink, once you pour the water down to the sink, you don't have any water left, or let's say juice. Or let's say you're trying to teleoperate, putting away dishes into a dishwasher. If you drop the dish and it breaks, well, all of a sudden you have to go out, to a store and buy a plate again. So, there's a lot of problems with real world teleoperation that can be solved with logistics and management and, good system design, but inherently there are a lot of fundamental limitations. On the other side, simulation is, answering that bitter question, the bitter statement, that Richard Sutton put out, everything that's scalable with compute ends up winning. And I will argue that simulation is exactly the answer to that. Right? The number of frames of data you can generate per second in simulation is scalable by compute, not by humans. And this is a big proponent for why I think simulation is so important. This is in addition to the fact that, if you want to teleoperate in simulation or generate data in simulation, you can change anything at any time. Like for example, if I want to change the lighting to be nighttime, I don't have to wait for nighttime in the real world. I can do it instantly. If I want to automatically check if my generated data is successful data or failure data, I don't have to label it with a VLM, or I don't have to label it by hand. I can write code to generate that information. Or you can use VLMs to write code, that's also possible. Another answer is also just like, reducing costs. A single GPU, right, is a couple $1,000s, generates infinite data for you. You can switch to robot embodiment at any time. But, to buy one robot, you need to buy like 5 GPUs worth of money, right? So yeah, fundamentally, physics limit a lot of the scaling possibilities in the world. And a lot of big companies now like Tesla and whatnot, they're going to try to scale teleoperation. But at a certain point, I will argue this is still never enough data. even if you had like many years of time. And this is not even getting to complications of like ethics and human privacy to try and collect real data in like someone's home, for example. And even then, one of the big plus sides of the real world data is really like, there's data diversity. I can take a video of my house. I can take a video of anyone's house and it'd be pretty diverse data. But in simulation, you kind of do some manual engineering. But I will argue the kind of negative sides of data diversity in simulation is being tackled. And I'll show some of the ways we are tackling it in ManiSkill. But there's also a lot of interesting like AIGC research from my group at Hao-Su's lab, trying to tackle this data diversity problem. Yeah. Another motivating factor I want to point out is a lot of people worry about simulation because they think simulation data is fake. How could you possibly train on it? Well, the first thing I'll mention, and from an intuitive point of view, is that humans, learn from simulated or fake data all the time. If you ever went to learn to drive a car or if you learn to fly a plane, you're often going to do that in virtual reality first, in VR. And humans all the time are learning from visuals or text without actions. And this could be like, say, a manual on how to repair a bike, or like animation videos or cooking videos on like Bilibili, right? And I will say the same for simulated data. Simulated data is not perfect, it's imperfect, but there are still learnable signals from the generated synthetic data that you can still train on. And this is actually quite possible. A lot of new VLAs, some of the best new VLAs are actually doing this exactly. And I'll lightly kind of cover them. So the recent RDT-1B model, which came out from Tsinghua, 5% of the data is actually from our simulator, ManiSkill. And just from conversing with the authors a couple of weeks ago, they said that having the data has helped their model quite a bit as opposed to not having it. And a lot of them are now exploring using more synthetic data generation to try to improve their models. The recent latent action pre-training model, LAPA, this is from UW, they also do the same thing. They have a large pre-training stage where they learn latents from videos without actual teleoperated actions. So I would say the best new VLAs that can do good pre-training on these internet-sized datasets as well as synthetic datasets will probably do really well. And it's a very interesting side of research to explore how can we get that data in the first place. Any questions in the meeting from anyone about this? Okay. So I'm going to start kind of going to ManiSkill3, which is kind of the main topic of the presentation today. Basically what I and my team have been working on for over a year now. And this is like a quick table from our recent ArcSiv publication, or not publication, sorry, our recent ArcSiv paper that we put online a couple of weeks ago. Very high level overview of comparisons between ManiSkill3 and different benchmarks. But the key kind of salient points is really that most past simulators compared to ManiSkill3 often only support a very narrow range of scenes or tasks. Like for example, Habitat and Omni Gibson, like Habitat only has like one interactable scene where you can pick and place objects. AIT4 has a lot of scenes, but you can't do low level manipulation. Omni Gibson has a bunch of closed source scenes, but it's really slow to run. And a lot of these problems are things that we're tackling in ManiSkill3. And another big problem for a lot of past benchmarks is a lot of them lack demonstration data. The only ones with pretty good demonstration data is really just our benchmark, the recent RoboCasa project, as well as RL Bench, which is the classic simulator. And another big problem is a lot of these benchmarks kind of lack a lot of tools for diverse data generation, which is, I will argue in the next few slides, of how important it is for scaling up the diverse data. Yeah, you guys can ask questions in Chinese too. I can mostly understand Chinese as well, or Jeremy can help translate it for me.
Yeah, thank you.
Yeah. Okay, so I'm just gonna go over some quick highlights. The first main feature that you guys might have seen before is that now, compared to past versions of our simulator, we actually have GPU parallelized simulation now. So our speed is on par with Isaac Gym. It's the same speed, actually. Both ManiSkill3 and Isaac Gym, or also known as Isaac Lab, all use the same physics engine. So there's no difference in speed anymore. The physics realism and speed is the exact same. The only difference is really on the rendering side. But we have the same features as them, but the main difference is our simulator has a lot of tasks. So this is an example of training a RL policy to pick up a cube with 1,000 plus parallel environments rendered here. And we have pretty much state-of-the-art parallel rendering speed and memory results. I'll show exact numbers later. But yeah, this is one of the big features of ManiSkill3. This GPU parallelization is pretty important, particularly on the topic of data generation. A very common road of research recently is like, how can we train policies and simulation to then generate more synthetic data for us? One of the ways that people who worked on the RDT1B project are exploring, for example, is can we train RL policies and simulation or imitation learning policies with online data collection, and then roll that out to generate more data for us. So that's one of the big reasons why I want to support GPU parallelization is just fast training, right? Another big feature is we have way more tasks, demonstrations, robots, and scenes spanning a lot of different categories, much more than any other benchmark. So we have like mobile manipulation, dexterous manipulation, humanoids, locomotion. We have drawing and cleaning tasks, all GPU parallelized. We even have vision tactile environments. So there's a lot of diverse tasks and tasks, demonstrations, and robots that are in our benchmark now that you can use to generate data for, to like do any kind of training you want or do research and reinforcement learning. And while this project does not work on contributing, let's say, generated tasks, like language model generated tasks, like other recent work, like GenSim2, a lot of these tasks are kind of hand engineered at the moment. My lab and some other collaborators are also looking to generated simulation, where we can use this framework to easily build and generate via language models and VLMs, like infinite different tasks with like success conditions. But the first prioritization for ManiSkill3 is really just to build a fast, realistic sound foundation for simulation. And yeah, we also have now, I believe, the most quantity and diversity-wise of different interactable robotics scenes. So in this case, ManiSkill3, the latest ManiSkill3, has 3 scenes now. Replica CAD from Habitat, which is from Meta. We also have Alan AI's Thor simulator scenes, and also the recent RoboCasa project. All of those scenes have been imported to ManiSkill3, and all of them have been GPU parallelized to run much faster than the original simulator speeds. So in all these scenes, you can spawn a robot in there, try to grab objects. Many of these scenes have articulate cabinets as well, so you can simulate, actual cooking or kitchen, stuff like that. And a lot of these can be used for massive synthetic data generation for future downstream training of RL policies, VLAs, and more. Another big feature that we've been very excited to share with everyone is we support something called diverse parallel simulation, or also known as heterogeneous parallel simulation, for generalizable robotics. So one of the big goals of ManiSkill3 is like, we're trying to answer the question, how can we help scale up simulation for embodied AI? And one of the big problems is data diversity. If you ever use Isaac Lab or some of the other GPU parallelized simulators, one of the big problems they have is that in all the parallel environments, the objects are almost always the same. They might have similar topology and maybe some random textures, but inherently they're all the same object. Different to like Isaac, for example, in ManiSkill3, we are able to simulate entirely different cabinets and objects and different number of objects in parallel GPU simulations. And we provide a very simple object-oriented API to do this. And what's good about this feature is that this allows you to train generalizable policies, policies that can generalize across different cabinets, right? Different objects and such. And that's kind of the whole point of ManiSkill, which is training generalizable robot manipulation policies. And now with GPU simulation now, like this open cabinet drawer task, this task used to take maybe a couple hours to train. Now it trains in about 20 minutes. So we've massively reduced training time. And you can also train and solve this task in a few hours from vision-based instead of weeks now. So in addition to just, randomizing articulations, we're also able to, completely have GPU parallelized scene randomization. So each of these apartments in here are a little bit different. This is from an ongoing project that's in submission where we have a GPU parallelized simulation of like thousands of different apartments. And in each one, we have a little mobile robot just trying to solve a task of some kind. And we have another example here. This is RoboCasa. The RoboCasa project from UT Austin, NVIDIA has been imported into ManiSkill3, and we can GPU parallelize, render, and simulate every one of these. even if each of the apartment shapes are different, the objects are different, we can simulate them all together, and you can train on all of them at once to get generalizable policies. Someone asked a question just now. This video, parallel simulation means different robots in different scenes or different robots in one scene. So an example I'm showing you right now of RoboCasa, this is different robots in different scenes. So you see that every apartment or every house in here shown is completely different. Different textures, different materials, different numbers of cabinets, different objects completely. An example, this slide with the replica environment, it's a little bit harder to see, but if you zoom in, each of the apartments are a little bit different. And they're all doing different tasks, actually. They're all picking up objects from different places of the apartment. So we have many levels of parallelization possible in this case. You can parallelize the number of robots, you can parallelize the number of objects, you can also parallelize the entire scene itself. Yeah, and it runs pretty fast. I'll share some numbers very soon. And this is like a close-up of one of those. So this is one of the apartments. Just an example. We've improved upon the original habitat simulator to use low-level mobile manipulation. And this is from an ongoing project where we use reinforcement learning to train on depth images to like learn and pick and place in a house. Yeah. Okay. Last big feature, all of this is already open source. We've been open source for years, actually. The latest version of ManiSkill has been open source for about half a year now. And we've been creating a lot of great community support. Out of all the GPU simulators that are not backed by companies, we're probably the most popular one now, which is great. Nearing 900 stars on GitHub, which is great. And every part of our tech stack is basically open source, which is a bit different from Isaac, which currently is partially closed source right now. So all the tasks and environments and like reinforcement learning, imitation learning code, all open source on ManiSkill. ManiSkill is built on top of a simulator called Sapien, which uses PhysX. Sapien's code is also all open source. So like our parallel rendering and simulations, all open source. So you guys can check it out. Okay, so just some example numbers. We are not the only player in town these days to do parallel rendering. Isaac Lab also has recently introduced this feature about a few weeks ago. But even then, we are still much performant. So on an example, very simple scene, which is a cart pull task, a classical control suite task, we outperform Isaac Lab by quite a large margin in terms of memory and FPS, frames per second. And we also support, doing all of this while rendering RGB, depth, and segmentation data simultaneously. So compared to Isaac Lab, when we're rendering, like, say, a realistic camera size of like 640 by 480 pixels, the same size used in the Google data size for robotics, we can render easily upwards to like 10,000 frames per second on a 4090, which outperforms Isaac Lab by about 2 to 10x, depending on how many parallel environments you use. And we note that the memory efficiency is also much better than ManiSkill, which enables users to run RL policies completely on the GPU without easily going over memory limits. So like if you're using SAC even or PPO, you can put all your image observations on your GPU and you don't have to worry about the simulator taking up too much memory details. 2 questions in the chat, let me answer them real quick. Is the proposed simulator support convenient collision detection, such as collision avoidance arm reach task? Great question, we do. We support 2 kinds of collision detection. There is what I call net body force detection, where you can query with the API the net force acting on an object. You can also do pairwise force detection. So you can query 2 objects and check the force in between them on the GPU simulation. So for example, all our pick and place tasks, usually we check if the robot is grasping something by using the pairwise contact detection. And for a collision avoidance arm reach task, yes, you can write a GPU simulation for that really easily with our object-oriented APIs. You can, for example, just check the net force on your arm, and if it goes above 10 newtons, you can say it failed. Another question, why could ManiSkill do rendering so fast? Any technical details? A little bit hard to go into it because most of the details are basically on code and just very good engineering. Most of the rendering features is primarily on the Sapien side, but as a high-level overview of why it's fast, we use Vulkan, very modern Vulkan graphics rendering, and Vulkan already has some pretty efficient parallel rendering in some sense. Basically, with Vulkan, if you guys didn't know about it, Vulkan has essentially like a drawing queue We send all the draw requests sequentially, actually, it's fine. And Vulkan will draw all of them at once. Actually, if you want to know really the technical details, you should check out the Vulkan documentation code. Yeah. I think some other reasons why we can do rendering really performantly. I can talk a bit more about memory. I help optimize that a bit. So our rendering has a number of like different possible shaders. We've optimized the shaders a lot so that the memory usage is a lot lower. For example, we have a very minimal shader, which generates RGB depth and segmentation data, but we remove a lot of certain other data that's being generated in between to save on memory. For example, our default shader would also generate like normals and some other data that is usually not used. So if you get rid of those, get rid of the background data generation, it renders very fast. Okay. Couple more numbers. So the RoboCasa project, which was released a few months ago from UT Austin, the original one on Mujoko runs with 32 frames per second without rendering. In comparison, ours runs at like 1500 FPS without rendering and 900 FPS with rendering. And we are also looking to potentially making this even faster. Because in fact, the speeds I'm showing here is actually the speed on a CPU simulation. With the GPU simulation, we are looking to solutions where we can do CPU simulation and GPU rendering, parallelized rendering. But basically, we're running like 20 to 30 times faster rates than the original code base thanks to our highly optimized simulation framework and parallel rendering. Someone asked, does a fast rendering sacrifice image quality? No. So the original image quality of the renders in ManiSkill2 and ManiSkill1 is the same exact thing in ManiSkill3. The reason why rendering is so fast on some environments is because we actually have GPU simulation. So when you're doing GPU simulation, all of the environment state, like where the robot is, where the objects are already on the GPU. So transferring that to the renderer is instant. There's no CPU GPU device transfer overhead, so that makes rendering a lot faster than it usually is. Whereas if you look at a lot of Mujoko-based environments, Mujoko is a CPU-based simulator. They have MJX, but MJX doesn't have rendering yet. But their CPU-based simulator has to transfer CPU state data to the renderer to then be rendered. So yeah. I'll give an example with the render quality, but they're basically, here, I can show an example. This is an example of our renders. This is using our fast parallel rendering system. We also support ray tracing. I can show ray tracing examples later, but we have, yeah, basically just standard parallel rendering. This is an example of like, I think 1024 environments, RGBD, all being rendered with different numbers of objects in each environment. The render quality here is the exact same thing you would see from, let's say, Mujoko's CPU, Mujoko's renderer as well. Exact same quality. The rendering pipeline is about similar, very similar. Yeah. Okay. If you guys are curious more about like qualitative comparisons, I can share that a little bit later as well. Our ManiSkill3 paper has more qualitative comparisons with Isaac, so you can take a look at that. Here's another example. This is a locomotion task. These images being shown here are directly generated on a simulator with shadows and all that. This policy here, for example, trains in about 20, I think, minutes on a 4090. Trying to train this vision-based input in Isaac or other simulators might take hours or days, depending on how you set it up. And on the topic of like trying to help support scalable embodied AI, one of the big things that ManiSkill3 supports is really just a lot of domain randomization that you can't normally do easily in other simulators. So for example, for a GPU simulation of like, let's say the pick a cube stacking task, you can randomize camera poses and camera intrinsics and camera extrinsics, right? Across each parallel environment. So you can easily now train a pose invariant policy if you wanted to. And if you're not training a pose invariant policy, you can take your demonstration data and augment it easily with our tools. So the top row shows pose randomization. The lower row shows texture randomization. So in this push T task, the classic push T task that diffusion policy tests on, I've randomized the T color in all the environments. And these are just a sample of like 4 out of, let's say, like 100 of them or something. Yeah, and so with our kind of demonstration tools, ManiSkill has been building a lot of like demonstration management and manipulation tools. Easily lets you augment your data sets like this. Yeah. Another big feature about ManiSkill3 that we are also pushing out, which is kind of orthogonal to VLAs, is building lots of digital twins. The original project is led by Xuanling, another PhD in my lab, called Simpler. We basically integrated tools for building digital twins and training/evaluating of them. And the point of these digital twins is that you can evaluate your models that are meant to be tested in the real world in simulation instead. And the correlation of success rate between simulation and real world is about the same. And in fact, we've actually ported some of these digital twins into our GPU simulation. And so now you can actually evaluate like almost 100 times, maybe even 200 times faster than the real world in simulation now. And this is a project that was done in collaboration with Google, DeepMind, and Stanford, and is now one of the standard evaluation benchmarks for VLAs now. A lot of VLAs evaluated on this benchmark now. Yeah, so this is just an example. So we also support vision tactile simulation. So this is not integrated into ManiSkill3 yet, but we have partners at Tsinghua and other groups that have been building vision tactile digital twins. This is an example of a peg insertion and a lock opening task that requires tactile information to solve. And these are pretty high quality digital twins. You can learn more about it if you search VTAC challenge. And coming up very soon, we also have another project where we're working on some low cost reproducible vision-based sim-to-real setups. This is not done, but we're gonna be using like kind of cheap Hugging Face arms that you might see that cost about $100. And within, let's say, an hour or two, you can set it up and train things really easily. Yeah, questions in the chat. Let me go answer them real quick. So how about the quality of cloth simulation? And someone also asked how to use the ManiSkill to construct and load a soft body object. So for soft body simulation, this is not in ManiSkill3 yet. It is still in ManiSkill2. So I recommend you guys to look up ManiSkill2. The code for that is still up on our GitHub. We have a soft body coupled with rigid body simulator in there that has a bunch of tasks in the past. I don't know. I'm a bit soft body simulation is a bit out of my depth, so I can't really comment on the quality. But we've had multiple people use our soft body simulator before, so I think it should be fine. So yeah, we have. I'll refer you guys to ManiSkill2 for how to deal with soft body. Jinfei asks, regarding the image quality, how realistic the simulation is the Soto nowadays Isaac and ManiSkill? So when it comes to rendering, actually, all the simulators have the same image quality. There's actually not much of a big difference. I will show some examples. I can show an example here. Here, sorry, let me unhide this. So I can compare against Isaac Lab and ManiSkill easily. Is because we have the same physics engine, so I can model them a bit easier. If you can see, the top rows of all these images is ManiSkill, the bottom row is Isaac Lab. They look virtually the same, essentially. Yeah, they're virtually the same in terms of rendering. Not much of a difference. Isaac Lab's renderer is a bit different from ours. That's why the images look a little bit different. And that's also why Isaac Lab has noisy rendering right now. I don't know what's up with this renderer, but it's a little bit noisy. So it's not quite ready yet, the renderer. But in terms of image quality, like Mojoko and ManiSkill, same thing, no difference. And also, Isaac, ManiSkill also support photorealistic rendering. So if I show you the images from before, let's just give a couple examples. Like this is a photorealistic rendering here. Really, like photorealistic rendering is really just another word for saying I'm doing ray tracing, which is where you are shooting rays into scene and bouncing it multiple times to compute the actual light values or the radiance and colors. But to be honest, to get best image quality, it's all down to your quality of assets, not the simulator. That's why I usually don't talk too much about image quality. Because like, to be honest, like the render quality I have in the images here are pretty good. But Isaac could also do the same exact thing if you import it into Isaac. There's no difference at all. I think the only difference between Isaac and ManiSkill is that I think in ManiSkill is a little bit easier to generate these images, in my opinion. We have a much simpler and easier to install system. So you can get ray tracing capabilities with a single pip install, essentially. Okay. Yeah. Tristan asked a question. What is your idea of Fei-Fei's concept? Digital cousins. Can ManiSkill do something related to digital cousins? Yes, we can exactly do digital cousins very easily. Digital cousins, from my understanding, is actually the same thing as digital twins, but randomizing textures. So for example, we already have them actually. We already have these. In the RoboCasa data set, each of these apartments have like 20 different variants of them. So if we're given the same apartment structure with the cabinets in different places, you can randomize the texture of all of them. And that's the same thing as a digital cousin. So we technically have it already, I guess. Yeah. And for those who aren't aware of what digital cousins are, I think if I remember correctly from their paper, a digital cousin is like a digital twin, but with a lot of randomizations to augment the data set. So instead of just one digital twin with a single look or single view with like the same textures and colors and materials, we're going to have n digital twins to form a digital cousin where each of these digital cousins looks the same kind of, but is different in a small way. Like the texture is a little bit different, the friction is a little bit different, the color is a little bit different, maybe the robot embodiment is different. All of that's possible in our simulator. I'm showing an example here, for example. These are technically digital cousins, I guess. Yeah. Good question, though. Yeah. Digital cousins are a very nice idea. Okay. I have a few more things left to talk about. The big other feature from ManiSkill3 can be summarized on one page. We have a lot of useful data generation conversion tools. I think we're the only simulator that does this. So we have extremely lightweight trajectory data storage formats. So you don't need to store images at all. In fact, we actually store all our demonstration data sets as state information only. And we provide tools to then replay it to add in visual information. And it turns out adding the visual information on your own computer as opposed to downloading it is faster. It's also because our render is very fast. So you're better off, just regenerating it. We also have tools to, like, as I shown before, to like augment existing trajectories visually. So like randomizing textures, randomizing camera poses, all of that very useful for data augmentation and pre-training for models. Another big thing for ManiSkill3 is we have a ton of baselines. Not all of the Reddit baselines are just ready yet, but we'll be doing benchmarking on a number of state-of-the-art algorithms to further support the community's research into like the generally 4 large categories of robot learning approaches. I kind of roughly categorize them as online reinforcement learning, online imitation learning, offline imitation learning, or also known as behavior cloning, and then also sense plan act. Yeah. And the reason why we support so many is, one, we want to support the community and research in all kinds of directions. The second thing is, to be honest, I don't really know what is the best robot learning approach that's going to, really solve a lot of the problems in embodied AI, but we want to support all those directions. I would say ManiSkill3 is more focused as like a data generation tool of some sort, right? Generate data for RL or generate data for imitation learning. Okay. User Jam asks a question. What is the main gap between simulation and Unreal in visual and physical aspects at the time? Is it possible to alleviate the gap with ManiSkill3? I would say ManiSkill3 is the best position simulator for alleviating the sim to real gap. We've done a lot of investigation ourselves for doing that. So for example, we have the real to sim gap is covered quite well, where the simulation and real world success rates are roughly the same, as you can see in the top right chart here. We evaluated like a lot of different open VLAs like RT1, 2, Octo, etc., and the success rates are correlated. For the sim to real gap is also bridgeable. I think there's a lot of open research to investigating this. One of them is with ManiSkill3, it's easier to alleviate because you can do a lot of visual domain randomization that you can't do in other simulators. So for example, let's say you're doing push T task in the real world. You have a red colored T, but you don't know what the exact color is in simulation, right? So what you can do is you can train on 100 different colors of the push T, and all of a sudden your policy is invariant to the color of T, which is what you want for a sim to real transfer, right? You want to focus on the structure, not the color. So a lot of domain randomization ManiSkill3 can help with the sim to real gap. Not solving it, but it will help a lot. In terms of the physical sim to real, a lot of people have already done this with Isaac Lab, but basically a lot of like domain randomization on the controllers, which you can do, helps a lot with that. Like you can change the stiffness and the damping parameters, or also known as PD parameters of the controllers. So I wouldn't say the sim to real gap is massive yet. And the other point I want to mention is that even though if you're worried about a sim to real gap, you can still do a lot of research into robot learning if you use synthetic data as pre-training data. So some of the older projects that I just mentioned that just came out, like RDT and LAPA, they pre-train on a lot of like fake data that's not collected with a robot, or like data that doesn't look real. There's some visual gaps. Like RDT1B, 5% of the training data set is actually from ManiSkill itself. So yeah. Let's ask this question. Someone asked, is it necessary to introduce a law of physical embedding to make up for the gap between real and simulation? Can ManiSkill3 already handle it? Does this step require GPU to parallel in a large scale scene? Sorry, I don't quite understand the question. I don't know what the law of physical embedding means. Are you trying to say you want to learn a sim to real like model? Or sorry, I don't quite understand the question. Could you ask it again? Let's see. Yeah, so we have a bunch of baselines. We're trying to support all kinds of research, and we're accepting lots of PRs from people. We've had like 30 plus contributors now on an open source repo. And then, yeah, that's the end of the talk. If you want to start using ManiSkill3, we have a Google Colab you can start running, or you can download the code yourself. It's a very simple pip install, and then assuming your NVIDIA drivers are installed correctly, you can start using ManiSkill3 immediately. So you can scan the QR code on the left, and then I also have a Twitter. I'm more often alive on Twitter. You can follow me or DM me there. Yeah, or you can ask me questions in chat here as well.